Hi, I'm Cassie Esfo,
I'm Genevieve Simons.
And I'm Mason Palladino.
and this is our Common Cold presentation. The first thing we did when we were trying to figure out how to do this problem was trying to figure out the best model for our simulation. And we ended up picking model number 4 as the best one. And when the first thing we did was derive it, and to do that, first we moved it into separable form so that we could easily solve it in that way. And then we integrated both sides with respect to t. To do that, we had to use fraction decomposition on the left side, which made it a little bit difficult and hard to eventually get, but eventually got it. And we differentiated both sides, which left us with this mess, which we eventually had to get x by itself. And through just lots of algebra, we were eventually able to come up with this equation, which we found eventually was the best fitting equation to our data.
We had a few steps that it took to get this, to understand that this model was the right fit for our data. So you can see model 4, which is that x prime equals ax n minus x, is an autonomous equation, meaning that it doesn't rely on time. And so knowing that this was autonomous, we were able to find the equilibrium points, which are the spots where the differential equation model equals 0. And we found that those were x equals 0 and x equals 26. So we made this vertical sign chart and discovered that x equals 26 is a stable equilibrium point and x equals 0 is unstable. So you can see that the data, the family of solutions is going away from the x equals 0 point and towards the x equals 26, which, looking at the trend of our data, is pretty accurate. It's getting that S curve shape. So at that point, we knew that we were on to something with this model. And so finding that x is 26 is a stable equilibrium point, we plugged that back in for x and found that a is 0, which means that the solution our parameter a must be close to 0. So we also noticed that on this parabola of the data infected versus the derivative infected, the trend line of an parabolic x squared equation fits the data pretty well. And here the coefficient on the x squared is negative 0.0399, which is pretty close to 0. So again, we're finding that a is pretty close to 0. So we guessed and checked until we could optimize our differential equation. We wanted to get the root mean square error closest to 1 and the r squared value the lowest root mean square error and the r squared closest to 1, which we found when a was 0.0314. And when you look at the statistical model of derivative versus slope for the infected population, you can see that there's a linear trend here with an r squared value of 0.9304, which means that the data's derivative and the model's derivative agreed pretty well. If the model had been perfect, then this line, it would have been y equals x. But it's not, obviously our model's not perfect, but it's pretty accurate because the coefficient on x is relatively close to 1 and the y-intercept is relatively close to 0, which means that our model is pretty close to accurate modeling the slope.
Well, 4 was the best one for modeling this. 3 was the worst for fitting the model data. First of all, the differential equation was linear, and the derivative of infected was clearly not linear. It was a parabolic shape. Second of all, there's only one equilibrium point for the model, and it is at x equals 26. our data has clearly two equilibrium points at 0 and 26. 3, there is a difference in the shape of the curves. Our model has a very S-shape curve, while the model solution is more of a curve, just kind of a smooth curve. And the last reason why it's not the best fit for this model is because the RMSE and R squared values were not that good. Using the same methods as we did for Model 4, we knew the A squared value, or we knew the A value was close to 0. So fiddling with that, we eventually got it to the best it could be at 0.224, and the RMSE value and the R squared value were still at a ways away from being accurate. They were at 4.373 and 0.833, which is pretty inaccurate.
Since Model 4 was our best fitting model, there was definitely reasons for that, as well as reasons that it could have been a little bit better. And as we can see, the coefficient of determination is 0.9867, which is very, very close to 1. So we can tell already that it's very close to fitting. As there were other models that also had really high coefficients of determination that were close to 1, but those ones usually did not have a really close fitting shape for the derivative of infected versus data of infected, like this one does, where the R squared is also pretty close to 1. So it obviously had the right shape, and it wasn't linear, or like some of the other models, the parabola was super low or super high or something like that. Unfortunately, there were some ways that it did make the coefficient of determination not exactly 1. There were ways that it could have been better. Like here on these two graphs, you can see that the lowest and highest points of the data are a little bit lower and a little bit higher, just more extreme than our model had. So that was a little bit probably making it a little inaccurate, and it's the same for here too. Also, as you can see, so it does fit the shape pretty well. However, while the data derivative got to all the way to 7, the model only got to 5.3, while the other numbers were pretty close. But if we look down at this graph of the model of infected derivative, you can see that it doesn't go nearly as high, or it's not nearly as steep as the graph given by the data here.
How could these models be improved, though? How could we make it so the models have better fit, or the simulation itself was more accurate? First of all, we could do the obvious thing and run multiple simulations. Doing multiple simulations and averaging the results would give much more accurate data points. The second, we could improve the differential equation by adding more parameters to it, being able to shift it in the slightest amounts to fit the model better. To improve the simulation itself, we could make it more randomized by either using something like a die or a random number generator, using something to make it a little bit more random instead of flailing our mouse around. Another way to make it more to improve the simulation is making the spread a little bit more realistic, adding things like interactions in other locations besides common places, like people having visitors or people like having parties, etc.
Thank you for watching this video where we explained how the way that we fit our data to a differential equation model for the spread of the common cold. Hope this helps explain the way that the common cold spreads, and so that we can prevent it and be a little bit more prepared for cold season. Thanks for watching.